Limestones are one of the most amazing rock types out there for several reasons. They've been used for medical benefits, they're a valuable rock resource for industry, they frequently are reservoirs for oil, and they are associated with economically valuable ores, notably lead ores and zinc ores that also contain sulfides, iron, silver, gold, and other valuable metals. Limestones frequently underlie spectacular landscapes, and they provide to the geologists that are studying them insight into environments on the Earth's surface, dating back to nearly 3 billion years ago. What is limestone? Limestone is a sedimentary rock that forms in several different ways, but the chemistry is nearly the same. It's calcium carbonate, where carbonate means carbon with 3 oxygens, CO3. Here is the mineral calcite. It's the crystalline form of CaCO3, but when it occurs as a sedimentary rock, it's called limestone. And it has a number of different forms. In modern sedimentary environments, limestone is made up of 2 mineral forms of calcium carbonate. The first is calcite. This makes up hard structures in organisms like coral. The other form is aragonite, calcium carbonate in a needle-like form. These are frequently produced by calcareous algae. In the geologic record, though, there are other types of carbonates that are not limestone. For example, earlier in Earth's history, vast amounts of dolomite were formed. It's a lot like limestone. It's a sedimentary rock, but it has more magnesium in it. A test to tell the difference is weak 2% hydrochloric acid, where the weak bonds of limestone will effervesce vigorously, whereas you have to listen to the more tightly bonded dolomite to know it's reacting at all. Can you see it effervesce? Now the dolomite. It doesn't effervesce at all. The reason for the tighter bonds is the presence of magnesium in the dolomite. Another important carbonate rock that formed as a sediment in the past has iron in the place of calcium, FeCO3. This is siderite, which is an important iron ore. In the modern geologic environment, though, limestone is the dominant carbonate mineral. But even with the same chemistry, when you encounter limestone in the field, it occurs as a variety of different rock types. Commonly, animals will generate a limestone shell, and of course, coral will generate a rigid structure to house the colonial organism. Over time, these hard parts will accumulate and form fossiliferous limestone. Fossiliferous limestones get their name because they're fossil-rich, with a matrix of carbonate silt or mud surrounding the fossils. This one is made of brachiopods. This one is made of coral. Frequently, fossiliferous limestones form as a reef structure in shallow water. The Guadalupe Mountains National Park in western Texas is a great example of a Permian reef complex that is amazingly well preserved from 260 million years ago. Limestone muds form in a number of ways, but a common one is the production of aragonite crystals by calcareous algae. The aragonite is deposited when the algae die. Penicillus, for example, is a calcareous type of algae in Florida Bay that produces aragonite mud. This is the mud being deposited on the west side of the Florida Keys. Micrite is a limestone mud that has no visible fossil content. It is essentially the limestone equivalent of clay, and it's made up of aragonite that has been converted into calcite. They are very consistent, but occasionally they have fossils, like this micrite from Brazil. And here. A really fine-grained homogeneous micrite is called a lithographic limestone. Lithographic limestones got their name because they were used to make lithographic prints from the late 1700s to the early 1900s for everything from artwork to money. The fine-grained limestone was easy to etch, and the homogeneous nature of the rock provided a very consistent surface to print with. Iowa's Lithograph City Formation became an important source of lithographic limestone in the U.S. during World War I. Only later, when metal printing plates replaced lithographic limestone, did production worldwide cease. But you can still see exposures in the old quarries in northeastern Iowa. Lithographic limestones form in environments where there aren't many organisms, either crawling around on the sediment surface or swimming around in the water. Otherwise, the sediment would have fossils and wouldn't be quite as homogeneous. The Solnhofen limestone in southern Germany is a world-famous lithographic limestone that contains spectacularly preserved Archaeopteryx fossils, a fossil long considered to be the transition from reptile to bird. The theory is that lithographic limestones form in hypersaline environments where most critters can't live, so there's nothing in the water to consume the animal before it's buried. Chalk is a limestone made up entirely of microscopic planktonic shells. Plankton such as forams and coccoliths secrete calcium carbonate hard parts called a test. When they die, the hard part eventually settles to the sea floor. In the absence of any other sediment, the accumulating deposit is called an ooze. The White Cliffs of Dover, all 1,600 feet of them, are made up of coccoliths, deposited at about 1/16th of an inch a year during Cretaceous time, 70 million years ago. Creta, by the way, is the Latin word for chalk. In the old days, blackboard chalk was made of the rock chalk. The problem is that it broke apart easily and chalk dust was everywhere. Now blackboard and sidewalk chalk are manufactured from gypsum, a more abundant sedimentary rock and one that's easier to work with. In higher energy environments like shallow water or beach deposits, limestones can be made up entirely of shells. This is called coquina. Coquina is easy to identify and remember. Students love seeing it on a sedimentary rock identification exam. They always say it looks like a Rice Krispie bar. Coquina is a common rock type in Florida and is affectionately called the rock that saved St. Augustine. That's because the Spanish built a castle out of it, the Castillo de San Marcos. As the British settlements in the Carolinas began to expand southward, the Spanish had anticipated warfare. Coquina was abundant, light, and easy to quarry. Most importantly, coquina was soft enough to absorb the impact of cannonballs. Initially in 1702, and then again in 1740, days of cannon shelling had no effect on the walls of the fortification. The cannonballs either sank into the soft rock or bounced off. After 27 days of shelling, the attackers finally gave up. The last limestone I'll mention is oolitic limestone. It's made up of tiny spheres of calcite. Oolitic limestones, or oolites, form a lot like hail does. Hail forms as an ice droplet that is bounced up and down in the atmosphere. With each upward swing, ice is added to the concentric layers. Oolites are swept back and forth across carbonate banks, and as they change depth and water conditions, they grow by adding additional layers of calcium carbonate. Carbonate banks are just beautiful, and the process of forming them makes me say, ooh. One of the things about oolites is that every geology department in the country has samples from the same formation. It's the Miami oolite. The Miami oolite formed during a high sea level when most of Florida was underwater. The oolite now underlies the city of Miami. Every time a building is built in and around Miami, tons of Miami oolites are excavated and shipped off to geology programs around the country. The reason limestone is so useful to geologists in reconstructing past environments is because it forms under relatively unique conditions. It frequently forms as a result of organic processes, and the chemistry of limestone is affected by the chemistry of both the atmosphere and ocean water. Limestones rarely form in conditions other than shallow and warm salt water. There are some cold water carbonates, and in unique conditions, you can get deep water carbonates. But for the most part, carbonates form within, say, 40 degrees of the equator and in water that's less than 100 feet deep. The reason is that sunlight is an important energy source for carbonate-generating environments. Organisms that produce carbonates thrive in warm water with a lot of sunlight. It's true that under certain conditions, when warm water is supersaturated in calcium carbonate, limestone will precipitate directly from seawater. But geologically, it seems that marine organisms are responsible for most of the generation of the world's limestone. So if you think about it, limestones accumulate as a result of living organisms generating a hard part while they grow. And when an organism dies, that hard part is deposited, either as a limestone mud or sand. The generation of thick limestone deposits then is going to take an immense amount of time. For comparison, the Mississippi River adds detrital sediment, sand, silt, and mud to the Mississippi Delta at a rate of roughly 3 or more feet every 10 to 20 years. Limestone, by contrast, has a typical sediment accumulation rate on the order of 3 feet per million years. But this is amazing in a different way, considering there are limestone deposits that are thousands of meters thick. So limestones really are a good rock to think about deep time and a great place to look in detail at the history of the planet. Moreover, limestone has a lot of fossils. From a modern carbonate environment, you can infer that carbonates occur in warm conditions near the equator when they formed as rock. Finally, the carbonate ion that makes up the calcium carbonate in limestone is a geochemical treasure trove of information. Oxygen isotopes analyzed in limestones deposited as early as 1 billion years ago have been used to estimate the amount of free oxygen in the Earth's atmosphere. Essentially, free oxygen didn't exist prior to 2.5 billion years ago, around the time photosynthetic bacteria were established. By 1 billion years ago, free oxygen made up 4% of the atmosphere. And by 600 million years ago, just prior to the establishment of abundant life on the planet, free oxygen had reached concentrations of 18% of the atmosphere, not much lower than today's atmospheric concentrations, which are 21%. This isotope data provides a record of both atmospheric conditions and the extent of photosynthesis going on through time. So the slow formation of limestone and the accumulation of thick limestone deposits enable scientists to generate very detailed records of conditions in both the ocean and the atmosphere through deep time. There are some people doing some really interesting studies of limestone all around the world. People have also been using limestone in lots of everyday ways for thousands and thousands of years. Megalithic temples of Malta were made of different types of limestone, and they are over 3,000 years old. The Greeks and the Romans frequently used limestone for buildings. The Theater of Marcellus, completed in 13 BC, used limestone for the facade and arches. The Acropolis of Athens is an ancient fortress built 400 BC, with limestone used extensively for the foundations of its buildings. Of course, limestone blocks are still used as building stone, depending on the hardness of the rock. The types of limestone you'll see in buildings are based on the amounts of sand, clay, and secondary calcium carbonate that is deposited in a rock pores later. The secondary calcium carbonate is sometimes a really good secondary binder, in which case it permeates the rock more completely, while other times the secondary binder is only poorly cemented. Indiana is quite proud of its limestone building stone, which they call the nation's building stone. This is a white, pure limestone. that has very little sand or silt in it. The stone shows up in fantastic buildings. The Empire State Building, the interior of the Lincoln Memorial, the Washington National Cathedral, and the Pentagon all use limestone quarried near Bloomington, Indiana. Before Indiana limestone became so popular, there was the Joliet limestone from Illinois, which a number of buildings in Chicago are built with, including the water tower that survived the Chicago fire of 1871. Chicago was built on an ancient coral reef, and when you drive on Interstate 80 by the town of Joliet, you pass right over the quarry, which is cut into that ancient coral reef. Cement is also a product of limestone. It was previously thought the pyramids of Egypt were made of carved limestone blocks, but recent evidence suggests at least some of the outside and upper blocks may have been manufactured in much the same way cement blocks are made today. Romans certainly knew how to make a cement very similar to the stuff we make today, and they used it as mortar in building stones and for roads. In fact, cement hasn't really changed since Roman times. Now cement, together with sand and gravel, is used to make concrete. Concrete is the second most consumed product on Earth, behind only water. To make cement, you grind limestone into a powder and then heat it. Although cement is an incredibly important product, I should point out that the heating of limestone produces greenhouse gases. The manufacture of a pound of cement releases almost a pound of CO2 into the atmosphere. In fact, the manufacture of cement is the number 3 source of human CO2 after fossil fuels and land use. During heating, the carbonate ion is driven off and the calcium ion binds with oxygen and anything added in, including clay and silica sand. When the process, called calcination, is completed, you generate calcium oxide, calcium silicates, the calcium of the limestone, bonds with the silicate sand, and calcium aluminate, which bonds with aluminum in the clays, and a whole lot of CO2 is emitted. The process results in these lumps called clinkers that are ground up to be cement. The mixing of cement, sand, gravel, and water makes concrete. Calcium oxide, or quicklime, is also widely used in industry. For example, calcium oxide is used to make glass or to extract gold from quartz. Calcium oxide is also used in filtering water. In agriculture, certain types of limestones are used, depending on the chemistry and sediment size, as agricultural lime. Applied to soils that are acidic, agricultural lime will neutralize that acidity. Agricultural lime also results in the formation of more soluble nutrients and will help plants absorb phosphates, for example. In heavy industries, limestone is used to generate steel. Burning iron ore in the presence of limestone will pull oxygen out of the ore. The oxygen bonds with a calcium ion. Pulling oxygen out of the iron makes possible the generation of steel, which is more malleable without the oxygen. Limestone, processed into a powdered form, is used for many different things depending on the chemistry of the limestone, including fillers in paints and plastics and in cleansers. Some limestone powders are used to whiten printing paper. It helps make paper that bright white color. Limestone also shows up in stuff you eat. Purified calcium from limestone is added to foods like breakfast cereal as a calcium vitamin supplement. That purified calcite can also show up in antacids. In cooking, limestone water or limestone paste is used in batters for fried foods or for pastries. This is predominantly calcium oxide, CaO, but it's slaked with water. That is, calcium oxide combines with water to make calcium hydroxide, CaOH2, or slaked lime. Limestone water is also used for crisping up vegetables. Cucumbers prior to pickling are soaked in lime water to crisp them up. Another way of thinking about limestone and the concept of deep time is the study of landforms that develop on limestone. In humid environments, limestone will form a valley. The reason is that over long periods of time, limestone dissolves. Under certain conditions, a unique landscape that results from the solution of limestone is karst. The features that make up karst landscape include caves and sinkholes, which are also known as dolines. The word karst is used to describe a distinctive assemblage of landforms that form on soluble rocks. This term comes from the Kras region of Slovenia, just north of Trieste, where there's an abundance of karst features. Now, karst does not have to involve limestone. For example, in New Mexico, there's a spectacular gypsum karst landscape preserved in Bottomless Lake State Park near Roswell. But because limestone is the most common soluble rock, when you talk or hear about karst, frequently what you're referring to is limestone landforms. The solution of limestone is a straightforward process. In the presence of water, the calcium ion disassociates from the carbonate ion. When the carbonate ion interacts with water, the carbonate ion breaks apart and you end up producing carbonic acid and hydroxide ion. So it's not just water, it's water plus carbonic acid, and the carbonic acid further drives the solution process. For similar reasons, in places where rainfall is acidic, limestone can dissolve fairly quickly. But in most settings, the formation of karst takes time depending on the rock chemistry, mineral variations within the rock, temperature, precipitation, and biologic activity, including the production of organic acids. Karst can be made up of a number of distinctive landforms. These include valleys that have rivers in them. In some places, and in other places, the drainage flows below the land surface. Caves can form, and in an older karst landscape, as most of the original valleys and cave roofs have dissolved away, what may be left are uplands that are residual features left standing when the rock around them is dissolved away. A spectacular example is the South China Karst, a UNESCO World Heritage Site that demonstrates tower and cone karst spectacularly. But the fundamental and most prominent landform in a karst environment are the dolines. Dolines refer specifically to sinkholes involved in carbonates, and these holes form when limestone dissolves at depth. What usually happens is a fracture in the rock begins to enlarge because water flows through it and dissolves the carbonate. Over time, and depending on the depth of the fracture will enlarge to the point when the overburden of overlying rock and soil will collapse down into it. I also want to point out that the movement of groundwater is fundamentally faster in all karst landscapes. In non-karst landscapes, groundwater flows through sandstone at rates that are on the order of a foot or a couple of feet per year. But that's groundwater flowing through sandstone. Groundwater flow in karst landscapes can reach over a foot per day because water is flowing through fractures. This means that if a pollutant gets into groundwater in a karst environment, it will move very quickly. There would be little attenuation of the pollutant, and it will appear in water wells and drinking water frequently before it can be detected. I've found dolines with old appliances, pesticide containers, and even oil drums in the bottom of them. And because the doline will connect rapidly and directly to groundwater, this is a real threat to drinking water quality. Karst landscapes in the U.S. are found especially in central and southern Florida and parts of Alabama, Tennessee, Kentucky, and southern Indiana. Usually people are well aware that they live in a karst environment, but changing conditions can trigger a land surface collapse and doline formation. For example, a change in land surface drainage patterns can funnel more water into fractures at depth. This will both increase solution and flush some supporting materials out of cavities. The result is that what was a fairly stable substratum can become an enlarging hole, and you can get collapse. Another problem is adding weight to the surface of a karst landscape. If you put a large building over a solution opening, what was previously supported surface will now collapse. One of the weirder causes of collapse is just lowering the water table. Say a new industry comes in, starts pumping water, and lowers the water table. What was once a landscape that was supported by hydrostatic pressure is now a landscape over a solution feature, and collapse occurs. Buildings that are affected by Doling collapse are almost always condemned. This also leads to a myth that sinkholes are swallowing up cars or houses. After all, recovering things that collapse into dolines is very difficult. But what actually happens is the first thing that will fall into the doline is subsequently covered by everything else falling into the doline. But newspapers or online accounts will frequently quote observations of things being swallowed up by sinkholes. But nothing's been swallowed up. Objects have simply fallen down into the doline and been covered by more things. And that's how they have been buried beyond recovery, by subsequent collapse. Caves are another type of karst feature, and caves do provide another one of these great records of deep time. First, there's the development of the open space of the cave. Just like with dolines, groundwater flows along a rock fracture or fracture system at depth. The solution process enlarges those fractures, and gradually you develop the cave opening. When you're in a cave or looking at a map of a cave system, the fracture pattern that generated the cave system can be readily observed. Caves will follow fractures, and there may be nearby caves following a parallel fracture trend. Or there may be a cave forming in the unit below along the same fracture pattern, but there's an insoluble rock type between the upper and lower cave. Caves can change even if they are no longer getting larger. Groundwater saturated in calcium carbonate will cease to dissolve the limestone bedrock and begin depositing features inside the caves. These cave formations are dripstone features known as speleothems. The most familiar dripstone features are stalactites, which drip from above, and stalagmites, which build up from below. But there are also thin, delicate structures of varying shape called helictites, which seem to form in defiance of gravity. It's been suggested that capillary forces, a combination of liquid surface tension and adhesion of liquid to the surrounding material within a small space of the growing helictite, determine the direction and shape of the growth. All these features form as a result of calcium carbonate going into solution in groundwater as it makes its way down to the cave. Whenever the liquid comes in contact with the cave, then there is a change in partial pressure. Suddenly, the water is not being compressed by the overlying rock, and the calcium carbonate that was in solution precipitates either on the ceiling, the floor, or the walls of the cave. This is calcium carbonate from a cave. Although the same general chemical composition as limestone, it is referred to as travertine. In this second one, you can see the calcite crystals. Travertine is also found precipitating around springs, especially hot springs, and waterfalls. In addition to calcium carbonate, the waters that deposit travertine also pick up trace amounts of things like iron and manganese in the rocks in the soil. This results in the dramatic coloration of travertine deposits. Frequently, travertine is used for decorative stone purposes. In addition to being spectacular in both form and color, speleothems hold a wealth of geologic information. Again, it has to do with the presence of carbon and oxygen in the carbonate ion of limestone and travertine. Studies of oxygen isotopes in cave formations have enabled the reconstruction of climatic events on both a local and global scale. An important paleoclimatic observation is that speleothems don't form during cold intervals. In any place with a winter like Minnesota, the ground is frozen, and there is an absence of organic acids because there's very little vegetation above the cave. As a result, there's relatively little water percolating down and very little acid in that water. So speleothems don't form during colder intervals, providing a climate record similar to what tree rings provide. I have to leave you with an understanding that karst caves can be very dangerous. Certainly negotiating a cave is, or certainly should be, intimidating, not least because there are hidden dangers as well. Caves, like dolines, are closely associated with the water table. If precipitation occurs anywhere in a drainage basin of a cave, then that can mean you could experience a rapid change in cave water levels. Also, caves close to the ocean, as in the Bahamas, Belize, or in Mexico, can be influenced by tides, again with dangerous changes in water levels. Also, while spending time in a cave, you're breathing a lot of carbon dioxide. Remember, limestone is dissolving constantly, and wherever that happens, carbon dioxide is being produced. I know after a couple of hours in a cave, I begin to get drowsy, and that makes you more likely to make bad decisions. And that's a condition you want to avoid. In addition to carbon dioxide, you also get the formation of carbon monoxide in caves. There are caves that are known killers. So to be safe, join a caving club, tour a cave with a knowledgeable guide, visit state parks and national parks with caves. They are fantastic, but never go into a cave that you don't know well without an experienced guide to lead you. Limestone is everywhere in North America, and we'll see limestone again later in the course when we discuss groundwater. Limestone is also in our homes, where calcium carbonate is in a very slow war against us. It will build up in rings in toilets and sinks. But where it really appears is with heat. Calcium carbonate precipitates in hot water pipe junctures, coffee makers, water heaters, and so on. You should take care. Over time, your expensive espresso maker will fail if you let calcium carbonate build up in it. In the United States, limestones and dolomites frequently record vast amounts of time when the North American plate was near the equator. During much of the Paleozoic, 1/2 to 1/4 billion years ago, the U.S. was covered in shallow blue seas where limestones were slowly accumulating. In contrast, cave formations recorded the time when North America was covered by ice sheets, and in locations south of the limit of glaciation, we have an isotope record of the cooling and warming events that resulted in glaciation and deglaciation. So in addition to all the practical uses of limestone, the geologic information they provide us is just amazing.